Hi class, this is Russ. I'd like to continue our discussion for Module 2, where we're building an implementation of the Java bag interface. Now, in the previous examples, one from Module 1 and the one from Module 2 that I've developed for you already, um, we talked about using the array bag. So for Module 1 example, um, we we developed this array bag as the container for all of the items that will be placed in or removed from the bag. Okay, and in the module one example, we actually hardwired a set size for the array bag of 25 items, no more than 25 items, and that of course is kind of restrictive, and it probably, and as we said earlier, it wouldn't bode too well for some high-end online shopping carts such as Amazon or Fred Meyer's or whatever. So we then in the second video, Dennis developed another capability where we could redimension the size of the bag dynamically. So in other words, when in this particular case, we would add two items to the cart and then we would desire to add a third item, we could do that by redimensioning the array, by recapacitating the array. This is kind of a response to the old C# Microsoft .NET capability where you could, the string builder where you could recapacitate array sizes and other types of, or if you're familiar with the redim command in BASIC, Quick Basic or Visual Basic has a redim where you can resize your arrays. Well, that's what basically is going on here, the equivalent in Java. And so it necessitated our having to um, modify the add method of the functionality, and so we had this double capacity when the array was full, and the double capacity made use of the arrays dot copy of as a way of redimensioning the array size. But nevertheless, this is still restrictive in that we still have an upper bound, and not only do we have an upper bound for the limitation of the size of the array bag, we're using numbers, okay? And what are the criteria for these numbers? Well, there are no criteria, so it's arbitrary and it's not general enough. So there is yet another solution. There are quite a few solutions to this, and one solution makes use of what are called linked bags. And in a linked bag implementation, um, we don't use numbers at all to set the size of the storage for the items that can go into the bag. So a linked bag, we'll go ahead and make a class called linked bag, and I'll explain the technical details. So let's go File, New Class, and we'll make it a final class, public final, and we'll call it linked bag. Okay, linked bag. All right, and so the objective of this particular structure is that we're going to be able to add an ad hoc number of items to the boutique, and we're not going to be constrained by lower bounds or upper bounds. Okay, in other words, we're not going to use numbers. Okay, so here's our class, and as usual, it's going to be an implementation of the bag interface. So it's going to implements bag interface of generic class T. Bag interface T. Okay, and so our linked bag has to take on interface types of T. Okay, so so now we need to add unimplemented methods. So you see this red warning indicator. We need to add unimplemented methods, and so click on this link, and then it brings in all of the unimplemented methods. Okay, and now we need to implement those methods and possibly add more of our own. Now, so before I proceed with the details of the linked bag, let's recall from 372, Computer Science 372, what exactly is a linked list. And I have this example, I believe, if I can pull it up, of a linked list implementation. In this case, a linked list is, if you look at this particular diagram, so a linked list, this is called a singly linked list, and there are things called doubly linked lists, which we may work with during this course. I'm not sure yet. I'll check on that. But in a singly linked list, if you look at each of these objects, S, R, and Q, okay, S is basically an object instance of the boutique items class. In other words, S is something that we are going to put into a bag. And you have this arrow. This is another attribute of the class that references the neighbor, another class. So in other words, you have S, and then S references another object instance called R. So think of this as just nothing more than an array of items, of boutique items. And the caveat is that each item references its neighbor, an item next to it. Okay, in this particular fashion. So, like for instance, if I wanted to add, and take note of this URL if you want to go to the visualization. It's a pretty cool visualization. So if I wanted to add, say, um, uh, item W to my linked list, and so since it's a stack implementation, I'll go ahead and push W, and notice that W uh, enters into the linked list in a stack-like fashion. And if I want to remove an item, so it removes the first in, first out. So it's basically a FIFO stack type arrangement. Or if I wanted to, I don't know, can I remove R, or would it just remove the head of the linked list? Okay, so it just removes the head of the linked list. Okay, and so this is the model. This is the model that we will use to implement our linked bag. Note that there are no restrictions on how many items we can add to this linked list. There's no logical limit. Of course, there's a physical limit based on your computer resources, but there's no logical limit, and that's kind of nice to have. Okay, so let's proceed with the work that needs to be done. So hop back into Eclipse, go back into our linked bag class, and let's see some of the things we need to do. Okay, well, first of all, let me go back to that illustration again. Um, in this case, notice that these entities, we have the instance of the bag items class, and then a pointer to the next item in the list. So this is a list. So we call each component, each element of this list a node. Okay, so we're going to use a technique called an inner node development, or not check that, an inner class development. And so we touched upon this briefly in 372, what an inner class is. And so our inner class is going to be what's called a node. And nodes are just basically elements in the list, in the linked list. All right, so let me go in here. And so in the class linked bag, the linked elements are going to be called nodes. So we'll have a private class. Okay, so private class node. All right. And so the elements, each node, the data of each node in the list is going to be of generic type T. And so in our specific case, it'll be a bag items. Okay, so private T, and we'll call this data. All right. And so this will be an entry in the bag. Okay. And then, of course, now looking at the model, the visual model, notice that each node has a pointer to the next node, okay? And so we have to reference the next node in our node. So we have a private, okay, node next, okay? So this is kind of a recursive definition. We're using a node within a node, okay? And so this is the link. This is actually the link to the next node. All right. So kind of a clever use of recursion. This is in essence a recursive type development here. Okay, so we need our constructor, right? So we have a private constructor. So we'll have private node, and it'll be a non-default. So T, and this will be the data portion. Okay, this will be basically the class, the boutique items class, right? And so we will have this, okay, data portion. Okay, so this, and then null. So basically what this, so the way this works, okay, the way this is going to work is when you allocate a node, the data of the node will be an object instance of, right here, boutique items, okay? And then the next item will be nothing, okay, or null. Is that a semicolon or a colon? Okay, let me try putting a semicolon there. What's wrong? Why does it not like that? Create constructor node T. Oh, I need a constructor. Oh, I thought I did. Well, let's do it. Okay. Okay. It's got impatient on me. Okay. So, all right. So now this is the constructor here. Instead of um, instead of having an object, a generic object, uh, for this particular constructor, this constructor assumes that we take an existing object, bank items object, and we give it um, a neighbor, which we'd call next node. Okay, and so how does this work? Okay, so for this particular constructor, um, we have data is equal to data portion. Okay, and then next, okay, is equal to next node. In this case, next node is not null. Okay, and yeah, so that's all we need to do. So this is how you create a node um, that's being pointed to. So in this case, what we do is we create a node with a neighbor that's not null. Okay, and this is the constructor that we'll call to initialize the linked list with a single node. And this is the method, the constructor we will call to add. What this method does is it will add a node to an existing list. This is the addition of a node to. This basically is the when we check that when we add, we haven't done the add method yet. When we add a node to an existing list, okay, we call this constructor. When we don't have a list and we wish to initialize the list with a node, a single node, in other words, the list is null, but the list all of a sudden takes on a new node, we call this particular constructor. And we'll see that as we go through the methods. It'll make more sense. So this is the private inner class, okay? And this will be the storage for the linked bag. Okay, so now on to the things we need to do. All right. Okay, so now in our class, we need some variables, okay? So the first variable I suggest using would be private node, okay, first node. Okay, so this will be the node that starts the list, okay? And then, of course, then we need the number of elements in the list, number of items in the list. So private int number of entries. Okay, so I think this makes sense. All right, so the first thing we need to do is we need a constructor for our linked bag. So we have public um, linked bag, okay, and so the first node will be null until we, let's see here, first node equals to null. All right, so we have that. And then the number of entries is 0. And what else? Anything else? Okay, so that's our default constructor. All right. So one of the things we need to do is we need to check if the bag is empty. All right. And so how can we do that? So again, we can use that nice logical return format. We can say return true if number of entries is exactly 0. So we don't really need an if statement, just this is a Boolean expression. The double equal sign is a Boolean expression. Okay, so that's our is empty. So that's nice. Then we can get the current size. Okay, we can implement details for the get current size. So let's remove the auto-generated code. And so get current size would be return number of entries, right? Return number of entries. Okay, so we do that, okay? All right, so those two were easy. Let me check those off. So we've done is empty and get current size. Now we go on to add. Okay, so let's tackle the add. So add a specific item. Okay, now It's possible that you could add so much data to your linked list that you could run out of memory. Okay, so you could, so in your documentation is a possible error, potential error for this method, error, you run out of memory or other resources. Okay, but again, there's no logical limit to which you can add. Okay, so now what we want to do is we want to add to the beginning of the chain. Okay, so that means basically we're going to do a stack-based implementation of the linked list. Okay, we are going to do this. Okay, so remember this URL for visualization. All right, so let's see here. Add to the beginning of the list. All right, so now you see the importance of documentation. We could implement our linked list using a queue, okay? But in this case, we'll keep things simple and we'll implement our linked list in the form of a stack. All right, so what do we do here? So we need a node, new node, okay, is equal to new node, new entry, okay? And so that basically allocates the generic object instance, okay? And then we need the next. So in this case, new node dot next, okay? And what is that going to equal? That would equal to first node, okay? All right, okay. And then, so if the chain is empty, okay, so let's see. All right. Okay, so basically, new node references first node. So first node is null. Note, first node is null if the chain is empty. Okay, and just to clarify, this new node is going to be added to the head of the list. Okay, new node, I should write, new node is added to the head of the list. Okay, so in other words, it's going to be made the first item. Okay, all right, so now, okay, so first node, okay, in this case is equal to new node. So this solidifies the, okay, so this makes the new node at the beginning of the list. Let me check. Okay, yeah. So what's actually going on here, actually I got my comments. This will make it the head of the list, and the new node, what's going on here is that new node points to the list or chain. Okay, so this makes the new node point to the running list, and this makes the first node equal to the node that we're adding. Okay, so that's the way it works. Okay, so if the list is null, new node will point to null. Okay. Okay, so if first node is null, then the new node points to null, and the first node becomes the new node. Okay, all right. Okay, so that's the way that works. And then we bump up our number of entries. Number of entries plus plus, right? Okay, so we got that. And then we return, since this is a Boolean, we return true. Okay, so there's our add method. Pretty straightforward. Okay, so what can we add next? What other things? Oh yeah, we need the to array. Okay, so we need to retrieve all of the items in the list in the form of an array. Okay, so where's our to array? There we go. Here's our to array. So we need to implement the details. Okay. Okay, so it won't be too much different from the previous implementations. So we have, notice that I'm not having to run a check initialization. We don't care if the list is initialized or not. Okay, that was done in the constructor. So we have already eliminated some of the complexity. Okay, so now, just like we did before, we need to allocate an array. Okay, and so that's equal to a cast, generic cast, array cast of objects, right? New um, object number of entries, Okay, and so there we have our result, and now we have to do some sort of copying, right? So here's how we copy into the array. Int index is equal to 0. Okay, we use an index variable, and so we have our current node is equal to first node. So set a current node equal to first node. Okay, and we need a while loop. While index is less than number of entries. Okay, and the current node is not null. It's not equal to null. Okay, this is our iterator. We're iterating through the linked list. Okay, current node. Oh, I misspelled node. Sorry. Okay, current node is not null. So then we start copying the elements of the linked list into our result array. So result index, okay, is equal to current node dot data. So this basically takes the object instance, the boutique items element in the list, and strips off the pointer and stuffs it into the array of boutique items. Okay, and then we bump our index. Okay, what else? Oh, and then we have to advance to the next node, right? So current node is equal to current node dot next. Okay, and so now we visit the second node. Okay, and that's there. It basically does the copying, and then we return result like so. Okay, and so there's our toArray method. Okay, so that seemed pretty straightforward. It actually seems easier than the previous capabilities functions. Okay, and so we need a get frequency. Count the number of times the occurrence of a given object instance occurs in our linked list. So where's our get frequency? Get right here. So let's handle this. I think this is pretty cool stuff. It's very powerful logic. Okay. All right. So now, so the frequency of an entry. Okay. So int frequency is equal to 0. Okay. And so we have int counter is equal to 0. Okay. I'll show you what I mean by counter in just a second. So now we need to go node current node is equal to first node, like so. So we declare a pointer to the first node, and then while counter less than number of entries, okay, and current node is not null. Okay, what do we do? Okay, so we need to resort to our equals method, right? So if an entry, and we've already discussed how we number of what's going on here. Okay, check this. Okay, change my. Okay, so if an entry dot, and we've already defined our equals method from module 1. Okay, if an entry equals the current node dot data, okay, then we increment our frequency. Okay, and then and so we advance to the next node. Current node is equal to current node dot next. You know, in looking at this, we actually really don't need this. Okay, why do we need this? I mean, if the current node points to the first node and we just keep traversing the list until we hit null, I think this is redundant. I can't think of a reason why we need this, but just for good measure, we'll leave it in for now. But I think eventually a good thing to experiment with is just rip this piece out. Okay, rip this counter out. It just seems like a needed overhead. I'll check it as well. All right, so that is our traversal through the list, scanning for duplicate nodes. And then we just, all we do is return frequency, like so. Okay, okay, so what next? Anything else we need to do here to get this thing to work? Contains, okay. Um, yeah, we can work on the contains method. This might be a little bit involved. No, not too involved, I think. Okay, so contains. So in this case, we're querying for the existence of a particular node in the linked list. Okay. All right. So Boolean found equals false, just like before. Okay. And node current node equals to first node, like so. Okay. And while not found, and yeah, so now they're seeing the utility of not needing a counter. Okay, and we're still haven't stumbled upon null yet as we traverse through the list. If an entry dot equals current node dot data found equals true, else, and then I guess probably we can break. No need, once we find something, we don't need to go through the entire list, right? So just break out of the while. Okay, else what? Current node, go to the next item. Okay, and then that would be the end of our while loop, and then we just return found, which is going to be true or false. Okay, what else? What are some other things we can do? I guess we need to treat remove and other things. Okay, so suppose we want to remove a specific node from the list. I think I'm going to go ahead and call it right now for this particular video example, and maybe you guys want to give some thought to the removal operations from this linked list, and then I'll go ahead and address the removing capability in another video.